Yeah, thanks a lot. And especially I have to express my cordial thanks to the organizing and the technical team for inviting me to this beautiful conference. So I really enjoyed it, and I find the talk really excellent. I learned a lot here. So first of all, this is some illustration about the things I mentioned yesterday. So I think it's important for me to express my thanks to Toshi as a friend and a mathematical colleague. So here you see the organizing team of an Oberwolfach conference, well, almost 10 years ago now. And this is the drawing of Sophus Lie that's on the title page of the Journal of Lie Theory, drawn by my teacher, Karl-Hermann Neeb. Okay, so what I want to speak about today is also a little bit at the boundary topic-wise of this conference, but what I will try to do is sort of, when I move along, get closer to the representation theory of semi-simple, simple, reductive groups. So the idea is something like unitary representation theory started from physics, right? So it started from quantum physics when the state space is a projective unitary space, and then symmetries are modeled by unitary representations of groups. And then all this started with the Lorentz group representations, the theorems of Barkman and Wigner, etc. But then sort of the mathematicians took over and then developed harmonic analysis for reductive groups and all that. And somehow this branched away from physics somehow. And what I want to try today is describe some ideas how one could get in touch again on a different level, like trying to connect quantum field theory, as it is done in the context of operator algebras, with the representations of reductive groups. And I think there are many beautiful connections in that area. So the program of the talk is first explain what the structures are that show up in physics, and then how they lead natural to what I call Euler elements in Lie algebras, basically 3 gradings, right? Which many of you are well aware of. Then we will study inclusions of operator algebras and how we can deal with them on the representation theoretic level. And then we will see how these 3 gradings can be used to get geometric structures on which we can actually construct such nets. And then I will talk about these constructions and how they are based on distribution vectors for unitary representations. And in this area, there are many, well, I would say there are a few results, but many open questions which are quite interesting. Okay, so let me start with the first slide to fill you in a little bit on von Neumann algebras, if you are not familiar with that. So von Neumann algebra is a subalgebra, star subalgebra of operators on a Hilbert space, which is equal to its own bicommutant. So that's the simplest definition. My notation for the commutant is the usual prime notation. And in this context, one studies 2 types of interesting vectors. So in representation theory, one looks at cyclic vectors for representations, but here one also looks at a sort of dual concept, which are the separating vectors. And this means that the orbit map of the operator algebra on the vector is injective. One can actually show that separating means being cyclic for the commutant, so there is some duality between these 2 concepts. And then a cornerstone of the structure theory of von Neumann algebras is the Tomita-Takasaki theorem, which tells us something about the situation where we have a vector which is not only cyclic, but also separating at the same time. So this creates some self-dual situation. And what this theorem says is that this context creates some additional interesting structure. So first of all, it creates a conjugation, so anti-unitary involution, and a positive self-adjoint operator delta, such that these two operators are related by this so-called modular relation. And if I conjugate the von Neumann algebra with J, I get the commutant. So in a way, the commutant and the von Neumann algebra are of the same type. So they are almost isomorphic. And the most important part is that the modular operator defines an automorphism group of the von Neumann algebra by conjugation. Right? So one gets some dynamics for free from the state. That's dynamically viewed the main point here. So the easy part of the theorem is to get these two operators, and the hard part is to show that they satisfy all these relations. So this proof goes over 6-7 pages in all the textbooks that I've seen a proof for that. So it's really involved. But to get the operator, what one does is one looks at this sort of complex conjugation map, which is well defined because the vector is separating. And then one observes that this operator has a closure, and the closed operator has a polar decomposition. And then the polar decomposition of the closure produces these two operators J and delta. So that's easy functional analysis, but satisfying the other relations is more complicated. Okay, so with this background on von Neumann algebras, we can now have a look at the sort of physical context. So in algebraic quantum field theory, the idea is you have some space-time manifold M, whatever it is, and in this manifold you have many open subsets, which you can think of as laboratories in which you want to do experiments, you want to measure something. And in quantum theory, observables are modeled by self-adjoint operators on a Hilbert space, so you organize them in von Neumann algebras. So you want to associate to any such, say, open subset von Neumann algebra on some Hilbert space. And now one writes down a certain list of axioms that one would like to have. And here is the sort of abstract version of that. So one thing is that if you enlarge your set, you want to have more observables. Right? That's the isotony, that's sort of easy. Now the second is more subtle. So this prime notation, this prime notation here means that if you have a space-time manifold, you have some notion of causal curves or world lines of points in this space. And then you want to say that O1 is contained in O2 prime if you cannot connect any 2 points in the two sets by such world lines, by causal curves. So in a way they are separate. And if this condition is satisfied, you want that the two operator algebras commutes because there is no room for uncertainty, right? So they cannot talk to each other, the two domains, so things should commute. Now, the next condition, the so-called Schlitter property, expresses that you can measure the whole universe in every laboratory, basically. Right? So you can prepare any state in any non-empty open subset, and this means that the state, which you may think of as a vacuum state, should be cyclic for all the operator algebras that we have. Right? So you can produce the whole Hilbert space with this operator algebra. Now, the next condition is the kind of condition that we love to have. If we want to have a symmetry group, then it should have a unitary representation on the Hilbert space. And this family of operator algebras should be covariant in this sense. So when the group should act on the space-time, and when you move the open subset, that should correspond to conjugating the operator algebra. Okay, now the most subtle condition now is the next one. That's the so-called Bisognano-Wiechmann property. And this is now connecting the modular theory, meaning the Tomita-Takesaki theorem, with this kind of geometric context. So we want that there are some domains which are more interesting than others. These are so-called wedge regions. And for these regions, we want that the state is not only cyclic, but also separating. Right? And when it is separating, we have this modular one-parameter group. And we want that this modular group comes from the unitary representation of G. So that this connects the modular theory to our group. And the last condition is that this cyclic vector should be invariant under the group. So the group acts by symmetries of the system in a way. So that's very natural. Now, the question I want to consider here is, well, I want to assume that G is a finite dimensional Lie group. And what one would like to see is which structural implications does the existence of such a system have on the group? Where should we look for sort of examples? How can we construct families? And in particular, how can we find these mysterious wedge regions that we would like to have to connect modular theory and nets of operator algebras? Okay. Now, one important concept here is that what I would like to call an Euler element. So these are elements in the Lie algebra, sorry, that define a 3 grading by the adjoint representation, right? So I want that the element is diagonalizable and that I only have the 3 eigenvalues plus minus 1 and 0. And it turns out that these elements show up sort of directly from these axioms that I showed you. And this is expressed by the following theorem, which is sort of rather fresh from earlier this year. So suppose we have a unitary representation of a finite dimensional Lie group, say with discrete kernel, and a fixed unit vector for the group. For Neumann algebra, for which this vector is cyclic and separating, so we have the Tomita-Takesaki context, and then we assume that somehow the situation is stable under small perturbations by the group. And this can be expressed by this third condition C, namely that inside this sort of thought big for Neumann algebra M, we have a smaller one, which we can move with small group elements without losing the cyclicity condition for this vector omega. Sorry. Okay, and then the last condition is that we want to connect the group with the modular operator. So there should be some element of the Lie algebra for which the unitary group generated by the modular operator comes from our group representation. And then the fantastic conclusion is that if one has this, then this Lie algebra element has to be an Euler element. So this means that we know where to look for these modular groups. And what we get for free in addition is that we also get some information on what the modular conjugation does. It acts on the group like the involution that we get from the 3 grading, which has as a fixed point space the 0 eigen space, and it flips the vectors of which are plus minus 1 eigenvectors. So I think that theorem would pass the sort of Kobayashi test, I think, in a way, because it's a nice theorem which condenses some complicated information in a very simple, clear conclusion about the structure one has. So I really like that. Okay, so the implication of that theorem is that whenever we have this sort of axiomatic quantum field theory situation, one would apply this theorem to the algebra M, which is associated to a wedge region where we know where we have this modular group. And then we could say, okay, we take as n a subalgebra attached to a relatively compact subset of this wedge region. And then we know if we move this relatively compact subset by some sufficiently small identity neighborhood of the group, it will remain inside. And therefore, this condition C will be satisfied. And as a consequence, the generator of the modular group will have to be an Euler element of our Lie algebra. So basically, this means that in all interesting situations, geometrically, this context is sort of automatic. Okay, so the conclusion is modular groups come from Euler elements. Okay, so then we should take a closer look at what Euler elements are. Well, I think Toshiyuki Kobayashi in the 90s, he worked a lot on three gradings, on Lie algebras, and analyzed root systems and the corresponding geometry. And together with Vincenzo Morinelli, I took this up in last year, where we interpret these structures in terms of sort of algebraic quantum field theory and this kind of axiomatic. So the picture is quite simple. So say when you have a simple Lie algebra, you choose an A, maximal adiagonalizable subalgebra. Then you have the restricted roots. You choose simple roots. And then we know that every Euler element in the Lie algebra will be conjugate to something in the Weil chamber. And because it's an Euler element, the values of the simple roots could only be 0 and 1. If it's in the Weil chamber. And then one only has to, well, then it's also easy to see that at most one simple root can take the value 1, because otherwise you get eigenvalues 2, 3, etc. And then you have to check which sort of roots occur. And this can be done by looking at the highest root and then looking at which base roots have coefficient 1. Right? And these correspond to the red dots here in the linking diagrams. So basically, the red dots classify the Euler elements in terms of the restricted roots. Okay, so that's very nice and simple. Interesting conclusion is that for E8, F4, and G2, there are no 3 gradings. And there are also no 3 gradings when you have BCN as a restricted root system. Right? And you have 5 gradings, but no 3 gradings. So no Euler elements in the Lie algebra. Okay, now the next step is, now we sort of know which kind of structure we can deal with. So we would start with an Euler element in the Lie algebra and the unitary representation, and say for Neumann algebra on the Hilbert space, cycling separating vector, unitary representation of linear G, an Euler element which represents this the corresponding modular group, and we also assume that we have a conjugation which satisfies this relation, so it corresponds to the corresponding involution on the Lie algebra. Sorry. Okay, now then to understand these configurations of von Neumann algebras, it's important to understand how inclusions arise. So we have this isotony condition. So in particular, what we have to understand are inclusions among the von Neumann algebras that we get by moving M around with a group. Right? So we should be able to test when 2 of these are contained in each other. And this kind of information is contained in the semigroup. So any containment can be reduced to containment of this sort, that the conjugate is contained in M. Of course, what's also relevant in this context is the stabilizer group of M that's certainly contained in the semigroup. Generically, the semigroup will be the stabilizer group. So there may be no non-trivial inclusions, but in some cases there are. Okay, and we want to understand what the semigroup is. And one structural feature that we need to describe the semigroup is the positive cone of the representation. So it's all Lie algebra elements for which the corresponding self-adjoint operator is positive. Right? So that's a convex cone that we can associate to every unitary representation. And this we will need. And then the result looks as follows. So we write this regrading obtained by the Euler element in this way. And then the semigroup looks as follows. So again, we assume the representation as discrete kernel to make things natural. And then we produce two cones. So we have this regrading, and then we take all positive elements in the one eigenspace and the negatives of the positive elements in the -1 eigenspace. So this produces two convex cones. They lie in these billion Lie algebras T plus -1 of H. And the semigroup that we have to understand has, two interesting decompositions. It has a polar decomposition. The stabilizer group of M has as a Lie algebra the zero eigenspace. So we have this sort of symmetric Lie algebra situation. And this C plus minus cone is in the -1 eigenspace of the corresponding involution. So that's like polar decomposition. And using old results of Khalid Koufani from North Sea, one can also write this as a sort of Gauss-like, Driehaar-like decomposition, which is much more useful. So in this form, we have a billion semigroups, and in the middle, we have this sort of symmetry group. So the interesting point here is that one actually can determine the semigroup, and this one can by knowing that we are dealing with an Euler element. Okay, so the takeaway message from that is that if the semigroup is non-trivial, then the corresponding positive cone has to be non-trivial. So to have non-trivial inclusions, we need elements with positive spectrum. Right, so that's the message here. So the two conclusions we have so far is that modular groups in our context always come from Euler elements, from regradings of the Lie algebra, and inclusions among this sort of basic family of von Neumann algebras you get by conjugating, they come from the positive cone of the representation. Okay, now, as I also stated earlier, the problem now is to see how to construct such families of operator algebras and to see on which homogeneous spaces they exist. Okay, to give you an answer to that, we have to recall a little bit about the notation of concerning symmetric spaces. So the symmetric spaces we encounter here are causal symmetric, are causal symmetric spaces. Okay, so this structure we have seen a lot here. Symmetric space, and on the Lie algebra level, we have the pair of Lie algebra with the evolution. We write H and Q for the eigenspaces. And then to make it causal, what we add is a convex cone in the Q part, which is the sort of basic tangent space of the symmetric space. And to produce an invariant geometric structure, we want this cone to be invariant under the adjoint group of H. And when we have that, we can produce a field of convex cones on the symmetric space, which is invariant under the group. Right? That's what I would like to call a causal symmetric space. And that's sort of an abstraction of the kind of structures one has in physics, where one likes to study Lorentz manifolds. So we know that semi-simple symmetric spaces are typically not Lorentzian. I mean, basically, there's only de Sitter and anti-de Sitter space. But the causal structures you have in much richer families. So that's much less restrictive, and that's what one encounters here. Now these causal symmetric spaces, they come in two flavors that I would like to call compactly and non-compactly causal, or elliptic and hyperbolic, if you like. So non-compactly causal means that the interior of the cone consists of hyperbolic elements. Right? So that's one type. And then the opposite type is that when you have a cone whose interior consists of elliptic elements, so more things you see compact Lie algebras. And then, as usual, one has the duality of symmetric Lie algebra structures that you get by multiplying the Q with I. And this duality exchanges elliptic and hyperbolic and sort of produces a duality between these kinds of structures. So if one wants to understand the variety of all these compact symmetric Lie algebras, one can either focus on compactly causal or non-compactly causal, and then use the duality. Okay, I mentioned already the physical examples. So the only Lorentzian causal symmetric spaces up to coverings are de Sitter and anti-de Sitter, the irreducible ones. And these are the two spaces one finds in the physics literature, the sort of the curved ones. Okay, now the interesting theorem in this context is that, I mean, we have seen that these modular structures produce Euler elements in the algebras. And what I will show you now is that whenever you have a simple Lie algebra with an Euler element, you automatically get, in a very natural way, a causal symmetric space without having to choose anything unnatural in addition. So if you have an Euler, if you have an Euler element, it's a hyperbolic element, so I can find a Cartan involution which flips it. So it's contained in the P of the Cartan decomposition. And then the interesting theorem is I can now construct an involution and a cone which produces a non-compactly causal symmetric Lie algebra. And what I do is I take the involution defined by the Euler element that commutes with the Cartan involution, so the product is again involution. And this turns out to be sort of causal. And the corresponding cone is the cone I can generate it by the H orbit of the Euler element. So the Euler element will be contained in this Q subspace for the involution. And the H orbit looks something like a one-sheeted hyperboloid, so it generates a convex cone. So this produces a non-compactly causal symmetric space. And basically from work of Gester Olafsson in the 80s, we know that one can get a classification of non-compactly causal symmetric spaces from this construction. One has to be a little careful here with the uniqueness of the cone. So typically there are many cones, so you can enlarge this sort of minimal cone and get a bigger one. But these cones you can never classify in a simple way. I mean, there are infinitely many. But if you stick to the minimal cone, then you really have a bijection between orbits of Euler elements and isomorphism classes of infinitesimal non-compactly causal symmetric spaces. So in the original work, the perspective was completely different. I mean, it was much more from the compactly causal side, coming from invariant cones and Lie algebras. So what I developed here is a sort of different perspective from the Euler element point of view. Okay, so the consequence is that what I get is from Euler elements non-compactly causal symmetric spaces. So from the level of von Neumann algebras, this means that these axioms that we have automatically tell us, say at least for simple Lie groups, which kind of spacetime manifolds we have to look for. Right? So they produce from the Euler elements these symmetric spaces. Okay. Now, what I want to do next is explain how one would proceed to construct nets of von Neumann algebras on symmetric spaces, and more generally causal manifolds on which a group acts. So this slide will be a little heavy, but after that we can forget about the von Neumann algebras. We will also have to simplify things a little bit. So the context is, suppose we have this geometry, a G manifold with a causal structure, a unitary representation, and then we want to construct von Neumann algebras. And the idea is one wants to split this construction into two levels, which the physicists call first and second quantization in a certain way. So the upper level is sort of the finite dimensional geometry. So think of M as a symmetric space, causal symmetric space, if you like. So in this symmetric space, we have open subsets. And instead of going directly to von Neumann algebras, we want to do an intermediate step, just first associating to these open sets real linear subspace in some Hilbert space. So this is something much simpler than a von Neumann algebra. So that would be this passage here. So we want to associate real subspaces in the Hilbert space on which we have our unitary representation. So from the physics perspective, the representation is the so-called one-particle representation. So if you know Wigner's definition of an elementary particle, it's an irreducible representation of a Lie group, right? And that's the one-particle level here we're dealing with. And the main part, well, from my present perspective, is to understand this passage. And then there are many functors of second quantization which you then can apply, and they preserve all the nice properties. So that's the second step here, which you should think of as a machine. You plug the structure from the one particle space in, and that produces the von Neumann algebras. So the gamma could be something like associating a symmetric Fock space or a skew-symmetric Fock space. So most important example is gamma H is the symmetric Fock space. So this is called the bosonic second quantization. Then the von Neumann algebra you would associate to a real subspace is, well, you use the so-called Weil operators. They are basically the representation of the Heisenberg group of the Fock space, on the Fock space. And then you have a real subspace of your symplectic vector space, which is your Hilbert space. And every real subspace, the image of the real subspace generates a von Neumann algebra. So if it's Lagrangian, it will be commutative. If it's not Lagrangian, it is not. And this is a process which is very well controlled, actually by quite old results by Araki from the late 60s, 70s. So there are many deep theorems about that, and this is very well understood. So what I will do in the following is focus on this first part. Now to put this into perspective, what this diagram describes is so-called free nets of von Neumann algebras. So they start from one particle spaces. So if one wants to do sort of deeper quantum field theory, one would have to understand interactions. And interactions means modifying this second quantization functor to something different. So these are the free constructions, but one has to start somewhere to understand these geometries. So I have 25 minutes, right? Yes. Okay, thanks. Okay, so I have to tell you what kind of structures we expect on the level of real subspace of a unitary representation. And there we have to specify three types. So first of all, we call a real subspace cyclic if it generates the complex Hilbert space by complex multiplication. Right? And then there is also a dual concept like being separating. So this means that it behaves like a Rn in Cn. So if I intersect with I times V is 0, and if I have both properties, I call it standard. Okay, so when I have a standard subspace, so these are the nice ones, then I can associate to this subspace also the moduli data that we have seen in the Tomita-Takesaki theorem, but in a sort of raw fashion without needing the von Neumann algebra. So I only need the standard subspace, and the idea is the same. So if it's standard, then this complex conjugation of its complexification with respect to V is well defined. It turns out to be a closed operator, and this closed operator has a polar decomposition, so I get its unitary part, or isometric part will be an anti-unitary conjugation, and the positive part is a positive self-adjoint operator, and they satisfy this relation. And the standard subspace will, as in the Tomita-Takesaki theorem, be the fixed point set of this involution. So the main point here is that this modular data in the Tomita-Takesaki theorem can already be obtained by this simpler structure, standard subspace, instead of a von Neumann algebra. And this is much closer to representation theory. Now the question is, how do we transcribe the axioms that we have seen for nets of von Neumann algebras into nets of real subspaces? And that's sort of easy. Now the context is we want to start with a V group, causal manifold, unitary representation, and now we want to write axioms for families of closed field subspaces attached to open subsets over, say, space-time manifold. Now, isotony is clear how to translate that. Now, locality now requires to interpret what the prime should be. Right? So remember, in the manifold, the prime means the open subsets cannot communicate. I don't have causal curves between them. And that would correspond to the von Neumann algebras to commute. Now, if you think of the Heisenberg group, then commuting of two operators in the Heisenberg group means that the symplectic form vanishes on the corresponding pair. And this is how we define the prime on the level of real subspace as the orthogonal, symplectic orthogonal space. So we want that if this condition is satisfied, then the two subspaces should be symplectically orthogonal for the symplectic form. Okay. Now, the Reschneider property is also translated directly. We want that the space is cyclic for any non-zero, non-empty open subset. Covariance looks even simpler in this context, so we can move the open subset with T and then move the corresponding real subspace. Now the Bichognano-Wiechmann property now states that for some region called W, we want that this subspace is standard so that we have modular group and a conjugation. And we want that in this case the modular group comes from some element of the Lie algebra, and we already know that it's good enough to look for Euler elements here. Okay, and then the perspective is that once you have that, you can apply any second quantization functor, and this will translate these properties into properties of the corresponding von Neumann algebras. So we only have to understand what happens on the level of the unitary representation, say the one particle subspace. Okay. Now, how do we get real subspaces? Now, the issue is that from the geometric perspective, one would like to construct real subspaces which are generated by finite dimensional H-invariant subspaces, and if H is a non-compact group, we know that we don't expect finite dimensional H-invariant subspaces in a unitary representation, so we have to look for distribution vectors. Okay, so yeah, I think here everyone is familiar with what a smooth vector is. Now the smooth vectors for a unitary representation, they carry a natural Frechet topology. So you refine the Hilbert space topology by taking semi-norms where you also plug in the action of the enveloping algebra. And once you have, well, and then by Gording, this is a dense subspace of the Hilbert space. So you have an inclusion. And this means that by dualizing, you get an inclusion of the Hilbert space into the dual space of this Frechet space. And by dual here, I mean sort of the antilinear continuous functionals, because the Hilbert space scalar product is sesquilinear. Yeah, this dual is called the space of distribution vectors. And the interesting thing is distribution vectors are not contained in the Hilbert space, but I can push them back into the Hilbert space by a so-called smearing operation. So if I hit them with test functions, they go back into the Hilbert space. And this smearing is basically the integrated representation. I mean, the group acts on distribution vectors, and if I integrate against the test function, it turns out that I'm back in the Hilbert space. Actually, I'm even further down in the smooth vectors, but that's not needed here. Okay, now the idea to get such nets now is as follows. One would like to start with a certain suitably chosen real space of distribution vectors, and then we want to associate to an open subset of the homogeneous space some real subspace of the Hilbert space. And this is done as follows. We apply to this real space of distribution vectors all test functions whose support is contained in O when it is moved down, projected down to the homogeneous space. Right? So that's a very simple procedure. And it associates to every open subset of the homogeneous space a closed real subspace of the Hilbert space. So that's easy. And from the construction, one immediately sees that two of the axioms are for free. I mean, it's clearly isotone. So if I have a larger set, I get a larger subspace. And it's also covariant for G. Right? So these are the easy conditions that are always satisfied. And now the difficult questions are, how do I have to choose E to satisfy the other conditions? Okay, and for that, it's important to understand what these mysterious wedge regions are. How could I guess what I should take for W? And again, here I can use the Euler element. So suppose we have a causal homogeneous space and an Euler element in the V algebra, then this Euler element generates a one parameter group of G, and this one parameter group acts on the homogeneous space, so I have a dynamical system. Right? So I have a flow on the homogeneous space. Well, knowing the outcome, I call it the modular flow because it will be connected to that. And the infinitesimal generator is often called the modular vector field. And now the interesting point is one can sort of read off what the natural candidate for the wedge domain is from this modular flow. You see, we have a causal manifold. So in each tangent space, we have an open cone. And then we also have this vector field. And now we can specify the domain of all points where this vector field is positive, right, in the sense of the cone field. That's an open subset. I mean, could be empty, and in some situations it actually is empty, but that's certainly natural domain, which is specified in terms of this flow. Now, here are some easy examples. So if G is the affine group acting on R as a symmetric space, then the modular flow would be just the dilations, and then the corresponding positivity domain of this of the dilations is just the right half line. Right? So that would be the wedge region in this context. Now for the Lorentz boosts on Minkowski space, the corresponding positivity domain is what people call the Rindler wedge. So this is something like a book-shaped kind of region, which is a quarter plane times an orthogonal sort of space-like subset. So this is something very explicit. And the same picture prevails when we go to the conformal completion of Minkowski space to the corresponding flat manifold. So typically these regions are easy to see in explicit situations. Okay, now let's start the whole business with the simplest class of symmetric spaces. These are the compactly causal ones because for them we can use highest weight representations to produce something. So that's the sort of elliptic context, if you like. Now, suppose we have a compactly causal symmetric space. So this means the corresponding cone is elliptic. And on the Lie algebra level, we want to start with a unitary representation for which the positive cone generates the Lie algebra. And this means basically it's a highest weight representation. Right? Unitary highest weight representation. You should think of G as a Hermitian simple Lie algebra. And in this case, we can easily specify a cone which defines a compactly causal structure simply by intersecting the positive cone without Q. And then the Euler elements we consider in this context now are those which are contained in H. So you see, in the beginning, I had Euler elements which were not specific in terms of the position with respect to tau, and in the classification of the non-compactly causal spaces, the Euler elements were contained in Q. Right? But here I assume that I have an Euler element for which the modular flow has a fixed point, so I assume the Euler element, now called H0, is contained in H, in the stabilizer group. That's an important difference. So in particular, know that the modular flow has a fixed point, so I have this sort of hyperbolic behavior around the base point. Now in this case, one can calculate the corresponding wedge region, and it turns out that it's the projection of a subsemi-group of the group into the symmetric space. And if you recall this theorem about the inclusions of operator algebras, there we have seen that the semi-group of endomorphisms of the operator algebra was of this polar type. So it had the unit group, which here is the centralizer of the Euler element, and some exponential factor in the Q direction. So the semigroup that we see here is precisely one of these endomorphism semigroups that we saw in this theorem. So and this connection made this context here much simpler for us, so we knew where we had to look. And then it turns out that the construction works well for any H spherical representation. So if we have an H invariant distribution vector in a unitary highest weight representation, we can take as E one-dimensional real subspace, then apply this procedure that you've seen on the last slide, and then the outcome is all the axioms are automatically satisfied. So for us, this was a sort of the first construction of non-trivial examples, so that we knew that something is going on here. Right? So what we don't have in this context is a classification of all E's for which the construction works, but at least we have some. Okay, so typical important special cases are the group type situation. The anti-de Sitter space is also non-compactly causal space, so to this space this construction applies very well. Now, on this compactly causal side, there are natural generalizations. First of all, these nets can also be pushed forward to these conformal causal spaces that I get by the flag manifolds that arise by conformal completions of Jordan algebras. So conformal completion of Minkowski space is the sort of physical example, but there are many others. And on these spaces, we also have nets where we see the wedge regions very well. And for the group case, we could also do this for non-reductive groups. Then the group acts simply by left translation on itself. The causal structure is basically given by the positive cone of a representation. And the wedge region is the corresponding semigroup that shows up everywhere in this business. Okay, so the interesting problem here is that, I mean, most of you are working with representations of semi-simple groups. And when I say highest rate representations, this is a very small section of this theory, right? And they only exist for Hermitian groups. So one would like to associate these structures to more general representations. And what I want to discuss now is at least a program or a scheme how to do that for any, say, irreducible representation of a simple E group. Okay, so that's very much work in progress. So with Gester Olafsson and Jan Ram and Aarhus. So let's start with a connected simple E group. We know that we need Euler elements. We can make them symmetric in terms of a Cartan involution. Then we know that this data produces a non-compactly causal symmetric space. Right? So that's the involution that we have to use there. So then the Euler element will be contained in the Q part. Right? It will be a tangent vector of the symmetric space. Now H will be an open subgroup of the fixed points. It should preserve the cone. And this condition is automatic if I take the identity component. Okay, M will be the corresponding symmetric space. We want to start with a unitary representation which, well, irreducible would be nice, but then we also have to implement these anti-unitary conjugations. So sometimes we have to double the representations to do that. So we assume that we have a finite sum, say, of irreducible representations. Okay, and then we always have a conjugation satisfying this relation. So we can implement the sort of tau H twist of the representation in the Hilbert space. And then we want to look for a k finite vector in this Hilbert space to this limit. Now, what happens here? Now, H is an element in the Lie algebra. This delta U of H is the corresponding skew-adjoint operator. When I multiply with I have a self-adjoint operator. Right? So what I do here is I use the analytic extension of the orbit map for the one parameter group generated by H in the imaginary direction. And we know from the analytic extension results of Krötz and Stanton, etc., that this analytic extension for Euler elements is defined on the interval between minus pi half and pi half, on the open interval, as a map into the Hilbert space. Right? So in this sense, it makes sense to look at this sort of curve. And then our conjecture is that this curve has a limit in the distribution vectors. So it can never end up in the Hilbert space itself, because this limit turns out to be always a hyperfunction vector. That's easy to see. And it will be H finite. Right? And the representation, if the group is non-compact, has no H finite vectors. So it certainly does not exist in the Hilbert space itself. Okay, so this is what we use here. So one knows from the theory of the ground domains of Riemannian spaces that orbit maps extend into the domain sitting in the complex group to domain which is right KC invariant. So this is unproblematic because we choose a k finite vector, right? So we can always extend to KC. And then that's the interesting part. That's a certain domain in P which consists of all elements for which the norm of ATX is smaller than pi half. So one has a very explicit description of that. And then one makes this G invariant because it's orbit maps. Okay, and then we know from a paper, I think it's 2004, which is more or less a tautological result because you have this holomorphic orbit map. The limit exists in the hyperfunction vector. So that's a very easy argument. And one can also, so the good point there is one knows that beta of V exists in some space, right? And then one can verify equivariance properties for the enveloping algebra, and in particular for the intersection of H with K. And one can easily show that this hyperfunction vector is H finite. And then what we want to know that this is a distribution vector. Now, there are automatic smoothness or automatic continuity theorems by Van den Ban and Delorme for the case when we start with a k fixed vector. Then we would end up with an H fixed hyperfunction vector. And this will automatically be a distribution vector. Now, what we need here is a sort of vector valued version of this result. So we asked the experts about that. And I mean, both Eric and Patrick confirmed that they believe that this is true, but no one wrote this up anywhere. So whenever you know a more general version of this automatic continuity, you would be very much interested. Okay, now here is another aspect of these limits. Actually, we are a little more bold even. I mean, we don't want only distribution vectors. We expect that we actually get distribution vectors for smaller groups, and in many cases even for this one parameter group. So to push them back into the Hilbert space, one has to smear only over smaller subgroups, which is analytically easier to deal with. And for that, we have this sort of theorem, which is basically harmonic analysis of one parameter groups. That's not so hard to derive. Namely, this limit will be a distribution vector for this one parameter group if and only if the norm on this group satisfies a certain growth condition. Right? So if this norm does not grow too fast, then well, if and only if this is the case, we have a distribution vector for the one parameter. Okay. Now, as I said, maybe this is too bold, but anyway, I mean, that's what we hope for. That these growth estimates are always satisfied, and therefore we would get, in particular, that we have a hyperfunction distribution vector. Now, if we have settled our conjecture 1, what we want to use for our construction is a finite dimensional k-invariant subspace, which consists of J fixed vectors. So J fixed vectors is not a problem because J preserves the k finite vectors and acts as an involution, so it has a large fixed point space. And then the interesting spaces are what we get by applying this boundary value map to such finite dimensional subspace. And then the sort of third conjecture tells you what we expect here. And we have bits and pieces for these results. This is always satisfied if we have an irreducible representation. Now what we expect is that the Riesz-Leader property is automatically satisfied. And that's because what we get from this picture is a realization of our representation in terms of boundary values of holomorphic functions. And for such boundary values, one has results like for Hardy spaces that any function is determined by the restriction of the boundary value to some small open subset. So that's the geometry behind the Reschneider property. And then the version of the Bisognaano-Wiechmann property we expect here is that if W is the positivity domain of the modular flow, then we expect that the real subspace associated to this W is actually a standard subspace for which the modular group is precisely given by the H. Okay, so time is up, so I think I jump to rest. And I think today is really the time to congratulate Toshi for his 60th birthday.